Slide 1. In the name of God, the most gracious, the most merciful. Slide 3. Introducing problem-solving agents. Hello, I'm AI Commander Ali Reza Kazabin, and in this part, we'll take a look at the first section of Chapter 3 in the AI book. Sometimes an agent can't decide just by looking at the current situation. It needs to imagine a few steps ahead and decide what sequence of actions to take to reach the goal. For example, imagine a robot needs to go from point A to point B, but there are several intersections on the way. It can't just start walking and decide in the middle where to go next. It has to consider all possible routes beforehand and pick the best one. We call this decision-making process problem solving, and the thinking process about routes is called search. For now, we assume a very simple environment, fully visible, predictable, and nothing new appears. Later, we will learn two types of search, one without any information about distance to goal, and one with some kind of estimate of how far we are. Slide 4, four-step problem-solving process. Looking more closely, an agent must go through these 4 steps to solve a problem. First, it must set a clear goal. Then it builds a model of how to get from here to there. Next, it tries different paths on paper or in its mind, and once it chooses one, it starts executing it. In a simple environment, the agent can blindly follow the path because it's sure nothing unexpected will happen. Let me give you an example. Imagine an agent traveling in Romania. It's currently in Arad and wants to get to Bucharest. It goes through these 4 steps. 1. Set the goal. I want to reach Bucharest. Without a goal, any movement could be aimless. 2. Define the problem. For each city, what are the options? From Arad, it can go to Sibiu, Timișoara, or Zirand. 3. Search through the paths to find the best way to Bucharest. For example, Arad, Sibiu, Făgăraș, Bucharest. This is our solution. 4. Finally, it follows the path step by step. In fully known environments, the agent can follow the plan without changing it. But in uncertain environments, it may need to change the path midway, making it a closed-loop system. Slide 5. Formal definition of a search problem. When we want to solve a problem, first we must define it formally and build a clear model. The main components are 1. State space, all possible states the agent can be in. 2. Initial state, where the agent starts, e.g. Arad. 3. Goal, where it needs to get to, e.g. Bucharest. 4. Allowed actions, what the agent can do, like moving from one city to another. 5. Transition model, e.g. if you move from Arad to Zirand, the next state is Zirand. 6. Cost function, for example, the distance or time needed for each action. When we perform a sequence of actions, we call it a path. If that path leads to the goal, it's a solution. If it's the least costly solution, we call it optimal. For example, in the Romania map, the path Arad, Sibiu, Râmnicu, Pitești, Bucharest can be a solution. We usually use graphs to represent this. Each city is a node vertex, and each move is an edge. Slide 6, representing the problem as a graph. To make it easier to visualize and solve these problems, we use graphs. States become points, nodes on the graph, and actions become the lines, edges connecting them. For example, in the Romania map, cities are nodes and roads are edges. If we want to go from Arad to Bucharest, the path is a sequence of edges. The total cost is the sum of the cost of all these edges. Slide 7. Abstraction and proper modeling level. Remember, the model we build is a simplified version of the real world. For example, we don't mention if the radio is on or where the police are, because these don't matter for route planning. This simplification is called abstraction. A good abstraction is simple but still valid and workable in real life. Saying go from Arad to Sibiu should be doable even with small differences like driving day or night. So far, we saw how to define a problem. But a key point is, we never model for reality because it's too complex. For example, if we say the agent is in Arad, we don't specify its car type, whether police presence, or fuel level because these don't affect route planning. We keep only what matters to solve the problem. This simplification is abstraction. A good example is a smart vacuum cleaner. It doesn't know the carpet color or the time of day. It just knows which room it's in and whether there's dirt there. If our abstract model can work in the real world, it's a good model. Another example, if we want to go from Tehran to Shiraz, the abstract model cares only about cities and distances. In reality, roads might be closed or no fuel available, but the model ignores those details and focuses on main paths. The simpler the model that still gives the right answer, the better. Final slide, summary. To sum up, for an agent to solve a problem, it must know its goal, define the problem as a simplified abstract model, search for a solution in that model, and finally execute that solution. All these steps help us find the best path through thinking, even before taking real actions. This is the core idea behind many intelligent systems, from robots and GPS to games like chess.
Thank you. Thank you so much for your time and attention. I hope that AI Commander Ali Reza Kasabin, was able to shine a light, however small, on the vast and stormy sea of artificial intelligence and help guide you a little further along your scientific journey.